Now in this module, we will be connecting the theoretical quantities, the Einstein's coefficients that we learnt about with experimental quantities, so that we will be able to compare the experimental spectra with whatever we have learned theoretically. So in this module, we will start with the learning outcomes and a brief introduction will be given. Then we will discuss the Lambert-Beer's law, which is the lifeline of spectroscopy, and compare with the experimental quantities whatever we have learnt about the Einstein coefficients, and then a brief summary will be given. Now after studying this module, you should be able to understand experimental recording of the spectra, its relationship with theoretical quantities derived so far. We will discuss the experimental recording of spectra and how the experimental quantities can be related to the theoretical quantities that we have studied so far. So we start with the Lambert-Beer's law, which is equally applicable to all kinds of spectroscopy and which forms the basis of the recording of experimental spectra. They are conveniently, experimental results are conveniently expressed in terms of Lambert-Beer's law. First we will talk about the Beer's law, which states that absorption of radiation is proportional to the number of absorbing molecules, and the number of absorbing molecules in solution is related to the concentration of the absorbing molecules. This is only true for dilute solutions of absorbing solutes in non-absorbing solvents, and then this is combined with Lambert's law, which states that the fraction of radiation absorbed is independent of the intensity of the radiation. In other words, equal fractions of the path length absorb the same proportion, not the same amount of incident radiation. These laws are strictly applicable to monochromatic radiation only. Now in this figure we have shown that the initial intensity is I0, and then it passes through this blue colored solution. We concentrate on a small length dl of the path length, which is L, and see what is the transmitted radiation, which we have denoted by IT. This is the radiation that is coming out. Now when you combine these two laws, you can derive what is called the Lambert-Beer law. According to Lambert-Beer's law, decrease in intensity, that is minus di, of monochromatic radiation, and stresses on monochromatic radiation, it cannot be any radiation, as it penetrates the distance dl, is proportional to the radiation density, that is the incident radiation at that point, the molar concentration C expressed in moles per decimeter cube, and to the thickness of the absorbing layer, that is dl, so that we can write mathematically that minus di is equal to alpha nu, where alpha is a proportionality constant, I C dl. This nu emphasizes that alpha depends upon the frequency. Alpha nu, we have emphasized that it depends upon the frequency because different amount of absorption takes place at different frequencies depending upon the Bohr condition, and this is called the absorption coefficient. It depends on the frequency of the radiation. It is highest at the frequency satisfying the Bohr condition, and when you integrate this equation, what you get is that minus ln I by I0 is equal to alpha as a function of nu, C and L. Now this is ln, which is natural log, but as you know, we normally prefer log to the base 10. So what you do is you use that factor 2.303, so that log I by I0 is equal to alpha nu divided by 2.303 into CL, and this particular quantity A is equal to log I0 by I is called the absorbance, and instead of alpha nu by 2.303, we have written epsilon nu. Epsilon nu is called the molar absorption coefficient, or it is also called the molar absorptivity, and also called the molar decadic absorption coefficient, because decadic means to the base 10 and A is the absorbance of the solution. Now this is the quantity that is measured in spectroscopy, in experimental spectroscopy. A is the absorbance. The molar absorption coefficient, that is what we had termed as epsilon as a function of nu, is more useful than absorbance since it is independent of the concentration and path length. Absorbance is proportional to both of them, but epsilon is not. The absorbance is a dimensionless quantity because the log of a quantity, and you cannot take log of units, and anyway I naught by I is dimensionless because both the intensities have the same unit. Concentration is expressed in moles per decimeter cubes in decimeter in SI units. Path length is generally expressed in centimeter, and usually it is 1 centimeter in most of the cuvettes that are provided with the spectrophotometers. So dimension of epsilon nu are decimeter cube per mole per centimeter, but by convention we do not mention these units. It is understood, if the units are not mentioned, that it is decimeter cube per mole per centimeter. Now there is another quantity that is also sometimes used, and this is called transmittance. It is the ratio of the transmitted to the incident radiation, that is I by I naught. The transmittance is generally expressed as a percentage, and it is I by I naught multiplied by 100. Now if the solution does not absorb at a particular frequency, absorbance will be 0 because I naught by I will be equal to 0 and all radiation is transmitted. That means that 100% transmittance is there. And the figure here shows how the absorbance varies and how the transmittance varies. They are inversely proportional almost to each other. Now they are complementary in nature, and suppose the absorbance of a compound is highest at a wavelength near 450 nanometer, transmittance is 0 at that wavelength. You can see from this figure that they are opposite to each other. Where the absorbance is a maximum, obviously the transmitted light will be the least and I will be very small, I by I naught will also be very, very small, it will be almost 0. Now the Lambert-Beer law is used to determine the concentration of unknown solutions. The linear relationship between the absorbance and concentration works only for dilute solutions, that is when the concentration or C is very low, but it is important to remember that at higher concentrations it can cease to be valid and relationship between A and C becomes nonlinear. So at concentrated solutions there is more interaction between the different solute molecules, and that is why it becomes nonlinear and it goes up to a constant value instead of increasing as the concentration increases. The absorbance does not increase with the concentration at high concentrations. So here is a small example. Suppose in a simple photometric experiment, to measure the concentration of a solution of potassium permanganate, you know that potassium permanganate is a highly colored solution. The spectrophotometer is 0 to give A is equal to 0 when C is equal to 0 by using a blank solution. So this is how we perform an experiment. First we take the solvent, so that we do not want the solvent absorbance to interfere in the value that we have calculated for the absorbance of the solution. We set the spectrophotometer to A is equal to 0 when C is equal to 0 by using a blank solution, which is the solvent. The absorbances A are measured for a series of standard concentrations C of potassium permanganate at its wavelength of maximum absorption, which is 522 nanometer. Then a best fit line of regression in a graph of the measured values of A against C gives a calibration line for a particular measurement. This is done. You can use any software like Excel, or you can use a graph paper to do that. Find the line that best fits the absorbance to the concentration. Now if you have a solution which you want to test, you find out the value of its absorbance under the same conditions, and from the value you can find out what is the value of the concentration of this unknown solution using the calibration line. So the absorbance A naught of the solution being tested is measured in this example 3 times and gives values. A naught is equal to 0.763, 0.741, 0.749. I use the term replicate values, means that if I repeat the experiment, I get the same value. The calibration values of absorbances A of the 6 standard solutions, that is C here is expressed in milligrams per liter, and at different concentrations you have found out what is the absorbance. And we also know that the molar mass of potassium permanganate, and this is equal to 156 grams per mole. So we find a best estimate for the molar absorptivity epsilon of potassium permanganate at this wavelength, assuming that the path length of the cell used to hold the solution is 1 centimeter. Now let us see what is the best estimate for the concentration. So like I said, you can use a spreadsheet program, and Excel is a one example of this kind of program, and you can find the line of best fit using one of its functions, which gives you a line of regression, and the slope turns out to be 0.0132 liter per milligram. And why you have got in liter per milligram is because we have not converted the concentration to moles per decimeter cube, which is the standard unit in epsilon. So we convert to molar concentrations, and the slope then turns out to be the slope that we got for liter per milligram by multiplying by 1000 and then by 158, which was the molar mass of the potassium permanganate that we have used, and this gives us a value equal to 2086 liter per mole or decimeter cube per mole, because liter is equal to decimeter cube in SI units. The molar absorptivity is thus epsilon is equal to 2086 decimeter cube per mole per centimeter. Now the average of the three observations was 0.751. Therefore, you can find out that from the slope the concentration is equal to absorbance divided by epsilon L, and you have already found the value of epsilon, and this gives you a value equal to 56.9 milligram per decimeter cube. This is how one usually does a Lambert-Beer experiment. We first verify whether Lambert-Beer's law is valid in that particular concentration region by making various concentrations, noting the absorbance, plotting the absorbance versus the concentration, getting the slope of the line, and you notice that the line passes through the origin because it does not have any constant point there, and that is why you can easily relate the absorbance to the concentration either by reading from the graph, or you can simply use the slope to find out the concentration. So this is the utility of the Lambert-Beer's law. Now how do we compare the experimental quantities that we have obtained with the theoretical quantities that we had obtained earlier? That is, we were talking in terms of transition probabilities, and we were talking in terms of Einstein's transition probabilities. So we connect the theoretical quantities with the experimental quantities. Theoretically, we found that the rate of transfer of molecules from a state I to another state j is given by Wij is equal to Bij into rho, and Bij is the Einstein coefficient of induced absorption, rho is the energy density of the radiation. This is what we had found earlier. Now each transfer changes the energy of the system by h nu. That means for every transition the energy of the system changes by h nu, and the energy density you can, because in Lambert-Beer's law we have the intensity, we do not have an expression for energy density, we convert it to intensity. Now using that we get a final result that A, I have used a bar over it to signify that this is in centimeter inverse, and this is given by Bij Ni h nu divided by 22,800 c square, and the quantity A bar is known as the integrated absorption coefficient. Now why do we need a new expression? We need an expression for the integrated absorption coefficient. You know that electronic transitions are band spectra, that is, they are very broad, because we have already seen that during an electronic transition both vibrational and rotational energy changes take place. Moreover, you have the Heisenberg uncertainty principle, which broadens the spectral lines, and that is why it is spread over a range of frequencies, and you do not have a single frequency. So the entire absorption band is spread over a region of frequencies, and you need to integrate the epsilon value as a function of the wave number and over the whole band to get the integrated absorption coefficient, which gives the total absorbance of the entire band. But because we have expressed the frequency as wave number, we get A bar, which is expressed in centimeter inverse. Now since the spread is over a range of frequencies instead of a single frequency satisfying the Bohr condition, you need to do all this. The integral is performed over the entire band, and epsilon nu bar emphasizes the wave number dependence of the molar absorption coefficient. So all the spectrophotometers usually express the absorbance as a function of nu bar or sometimes in terms of the wavelength. So it is very convenient to use the wave number because it is simply the reciprocal of the wavelength. Now this is directly related to the Einstein coefficient of induced absorption, which also is proportional to the square of the transition dipole moment. We have learned that theoretically this is the most important quantity because this governs whether a transition is allowed or it is forbidden. So now we have a bridge between the experimental and theoretical quantities. If you know one, you can find out the other one, and you see that Bij is directly proportional to the transition dipole moment square. The proportionality constant are all fundamental constants for which you can put in the various values and get an expression. So that means if you put in all these values, you will get the various constant, and the integrated absorption coefficient turns out to be directly proportional to the square of the transition dipole moment. And the frequency also expressed as wave numbers. It depends on that also because these are the only two quantities which are not fundamental constants, and this is here we take the wave number of the band maximum, and this is expressed in centimeter inverse, and the other quantity is the transition dipole moment, which is expressed in Coulomb meter units because it is like a dipole moment. Or you can rearrange this equation and you can compute the transition dipole moment from the experimental value of the integrated absorption coefficient. So what we want to say is that suppose theoretically you have found the transition dipole moment, you can take it square, you can find out what is the energy difference, find out the wave number, do all these calculations theoretically, and then you can predict what is the integrated absorption coefficient. Or you can find out the integrated absorption coefficient by doing an appropriate experiment and then relate it to the Mij square, which is the transition dipole moment, get these values from the, because you also know what the position of the band maximum is, what is the wave number at that point. So the only unknown is the transition dipole moment square. So the use of this equation allows us to determine one Einstein coefficient, and we have already seen that all the three Einstein coefficients are interrelated. If you know Bij, you can find out Bji, that is of the reverse transition, if you know the degeneracies of the both the levels, and Aji, the spontaneous emission coefficient, that also is related to Bji by a very simple equation. Now this is a very important quantity because the Einstein coefficient of spontaneous emission, it determines the lifetime of the excited state, and due to that it also determines the line width. That after the radiation is switched off, how do the molecules come back to the ground state? It is just spontaneous emission which is the only process that occurs during that time, and the decay of the excited state we know is a first order rate constant. Aji is a first order rate constant. That means that the rate of decay of the excited state, which we can denote as dnj by dt, this is proportional to the time, and the proportionality constant is equal to minus Aji. The minus means that the it is decaying, that the population of the upper level is decreasing. Now when you integrate this equation, it's a very simple process. You can find out Nj is equal to Nj naught, that is the initial value of the population of the excited state at the time the radiation was switched off, and exponential minus Aji into T. Now the natural lifetime of the excited state is given by the time taken for the excited state population to fall to 1 by E of the initial value. That is, it is the time, this lifetime is denoted by tau, and this is equal to 1 by Aji. So if you have determined Aji, you can also find out the lifetime of the excited state. So the absorption spectrum, just looking at the absorption spectrum, you can find out what is the natural lifetime of the excited state. Now there is also the Heisenberg uncertainty principle that we were talking about earlier, which governs the uncertainty in the frequency. That is tau, the time that the molecule spends in the excited state, the average lifetime of the excited state, that multiplied by delta nu is equal to 1 by 2 pi into tau, and this is the natural lifetime. So here is another example. We want to compute the natural line width and the Einstein A coefficient of a spectral transition whose lifetime is of the order of 10 raised to the power of -8 second. We've seen that electronic excited states usually have a lifetime of 10 raised to the power of -9 to 10 raised to the power of -8 second. So the solution is simple, that using this relation that delta nu is equal to 1 by 2 pi tau, we can find that delta nu will be equal to 1.59 into 10 raised to the power of 7 hertz, which we know is second inverse, and delta nu bar, that is the uncertainty wave number of the excited state, is equal to delta nu by c, and this turns out to be 5 into 10 raised to the power of -4 centimeter inverse. The Einstein coefficient thus is equal to 1 by tau, and this is equal to 1 into 10 raised to the power of 8 second. So in this module we have been able to relate what we have learned theoretically with experimental quantities that we encounter when we run a spectrum, and how we can relate the two, how we can get some idea about the transitions, whether they are allowed or not, and so on. So in summary, the experimental measurements in spectroscopy are based on the Lambert-Beer law. The law is applicable to all kinds of spectroscopy. It does not matter whether you are looking in the visible range or UV range, even for infrared spectroscopy it is applicable, and this is the basis of all kinds of spectrophotometers that are available. And comparison with the theoretical quantities and various Einstein's coefficients helps us to predict the absorbance from the transition dipole moment, and you can also do the reverse. Knowing the absorbance, you can find out the Einstein coefficients, as our examples we had shown just now, and the lifetime of the excited state can be measured from the Einstein coefficient of spontaneous emission, and this can be obtained from the shape of the experimental absorption curve.